All right, so let's try out a couple of continuity examples. So, for example, we're going to ask ourselves if this piecewise function, xy cubed over x squared plus y to the 6, oops, that's not 6, and otherwise 0, where the difference is just happening at the origin. And I want to check whether or not that's continuous. So the first condition that we talked about is that the function is defined at the x0, y0. And if we look at this, at kind of our breakpoint would be the origin. But there's definitely a definition. If I look at this piecewise function and I'm trying to evaluate at the origin, I would say, oh, it's 0. And I just want to make sure that if I'm heading towards 0, 0 using my other definition of the piecewise function, that I would get the same value as f of 0, 0 by the definition. And so I'm going to try this along a path that I think will make this easier on me. I'm going to say that I want x to be y cubed. The reason for that is because if I take y cubed squared, that'll become y to the 6th, and the sum in the denominator will simplify for me. So then my limit as I approach the point of xy cubed over x squared plus y to the 6th is going to become the same as the limit as just y goes to 0. And everywhere I see x, I'm going to replace with y cubed. That 6 is just a problem for me. All right. So when I simplify everything in the numerator, I've got y to the 6th. And in the denominator, I've got y to the 6th plus y to the 6th. That's 2y to the 6th. My y to the 6th cancel out, and I'm just left with 1/2. But that doesn't match the definition of 0 at the origin. So I know that this is not continuous. Because the limit as xy goes to 0, 0 of f of xy does not equal f evaluated at 0, 0. We can also use these rules to check when something should be continuous. So here's one I saw in your book that I liked. So I want to know what value of c will make this function that is defined by sine of x squared plus y squared over x squared plus y squared for all xy not at the origin and c at the origin. And I want to know what value of c will make this piecewise function continuous. So what I'm saying here is that my f of 0, 0, which is the point where I think continuity might break, is going to be equal to c. So it's definitely defined. And I just want to make sure that if I take this limit, I end up at the same place. That's this condition of continuity we talked about, that the limit and the function evaluation have to be the same thing. So I want to make sure that this is true. That would make it continuous. And I just need to solve for the c that makes that happen. So to solve for c, I need to know what this limit is. So let's go ahead and try to figure that out. So I'm going to try to take xy to 0, 0, sine of x squared plus y squared over x squared plus y squared. Now things get a little tricky here. This becomes easier if I try using polar coordinates. That means think about circles. X squared plus y squared shows up everywhere, but I know that that's just equal to some radius of a circle. So if I want to take x and y down to the origin, that'd be the same as taking the radius to 0 of a circle. Sort of think about, I'm getting closer and closer to the origin as I take smaller and smaller circles. And then I can replace every x squared plus y squared I see with an r squared instead. All right, so before I had something where as I go to 0, 0, I've got sine of 0 over 0. It's a mess. I still have something where I'm taking r to 0. So I end up at sine of 0 over 0, which I can't evaluate. But now I have a limit in terms of only one variable. And I know what to do when I'm looking at sine of 0 over 0. We had a whole lot of practice with that in chapter 10. I can apply L'Hopital's rule. So this is the same as taking the limit as r goes to 0 of 2r times cosine of r squared over 2r, just using in the numerator the chain rule and in the denominator a regular derivative. Unfortunately, as I take r to 0, this is still going to give me, cosine is 1 now, but 0 on top, 0 on bottom. So I'm going to have to do it again. And in the denominator, I'm going to end up with 2. So that's great. In the numerator, now I have to do like a product rule. So I'm going to take the derivative of 2r is 2 times cosine of r squared. And then the cosine of r squared derivative is going to be minus 2r sine of r squared times my original 2r. If that went a little fast for you, go back to it. I know we've been having some trouble getting back up to speed with derivatives, but they're going to keep coming back. And now if I try to take r to 0, my denominator's fine. This term is 0. This term isn't 0. So I know that I can evaluate this as is. I get 2 times cosine of 0 is just 2 minus 0 over 2. And that's just 1. So if I want this to be continuous, I need f of 0, 0 equal to c to be the same as this limit. But I just managed to take this limit. I know it's 1. So I know that I should have c equal to 1. Or I could just write it back up here. I could say, oh, must be 1 at that point in my function. And so those are the two different ways we can use this continuity, or two examples of it, one of them being to show that something isn't continuous, and one of them being to solve for a way to make something continuous. One last note, sorry. Hopefully you've noticed over the many limit examples we've done in these set of videos that a common approach to taking limits of functions of two variables is going to be to try and reduce it to a limit of one variable, because that's something you know how to do, or to make stuff cancel out in a nice way. So just try to bear that in mind. It is something that gets easier with practice. The trick won't always occur to you, so just do lots of problems and then you'll start to see the most common